So it starts from EC and have a square root like this. And we're counting its probability, f of e. Since now we still have the case that EF is below EC. So its EF should more like, so it should be half at EF and goes down quickly with the exponential in the below. So the actual carrier density is the area of this power. So to make it more clear, let's neglect the value of 0.5 just to make a better drawing. Alright. So let's consider something like this. Alright. This is f of e. So when this times two together, the density of state will rise first, then goes down because due to the quickly reducing occupancy. So this total area is the density of state, the total carrier density in the conduction band. So that doesn't matter about the shape when the energy is high. Although in the real case, the density of state might be quite different. Probably it should be something like this or something like that. Don't know. Yeah, because we only do the this relation comes from a parabolic energy assumption near the band edge. So it is accurate only near the EC. But since the probability of the occupancy at the energy higher than EC is very small, so it doesn't really contribute much accuracy to the inaccuracy of the system. So a fitting of the band structure with parabolic is good enough for most of the derivative materials. So this is because we know that it's state. So this area is the carrier density. Alright. So under equilibrium, the electron density should be equal to its hole density, since due to the charge neutral. If we don't have any doping inside that, so it would write down Ne is equal to P. Then we have equation 1 equal to equation 2. And you see, all the value here is given number. The only movable parameter is the position of Fermi level. So while these two equations equates, when you write down N is equal to P, then the position of Fermi level has to be determined. So that's why I say asking the position of the Fermi level is the same position, is the same question about how much carrier density you have in such band. Alright, so we have the in a 3D case, is the relation is in the square root of E minus EC. So if you put all the constant outside and leave the term with energy inside, we have an equation like this. Then we define two unit values. One is the distance between EF and EC. So this is the distance here. Let's evaluate this state, this energy, and let it be a unit volume. We try to evaluate how large width of this energy in terms of kg. So let this be V is equal to E. Okay, so it's in the reverse term. EF minus EC divided by KT. Since KT also in terms of energy. So V is a unique value. Then it becomes something the integral like this. A constant times 2 divided by pi. There's we have a reason why we pull out the 2 divided by square root pi for reason that we put inside. And an integral like this. Alright. And this integral is actually also you cannot solve it. You need a numerical approach. But we can make some reasonable numerical approach. And we call this integration called f divided by 1/2 So this is called the Fermi-Dirac integral. This. F of 1/2 in the subscript in the function of b is defined as integrating from 0 to infinity, and 1 plus e y minus e is b or u. Yeah, you'll lose the line. Okay, let's go b. And square root y. dy. Alright, so it's in terms of b. So why have a half here? Because we are taking the integral with second root. If it is f of 1/3, then probably it will be in the third root. Anyway, so this is a general net of such integral. It cannot be solved numerically, but we can make some numerical assumption. And the reason why we do that is why we pull out 2/pi here. That's because if the EF is larger than few kT, so this is C and EF. But this is large. For example, larger than 3 kT. What does that mean? That means f of 1/exponential EC minus EF over KT. So plus 1. This part is larger than E 的3次方 E cubic. And we swallow that this is much larger than 1. Yeah. So when EF is larger than EF is 3 kT less than the conduction band edge. When EF is much less 3 kT below the conduction band edge, we can approximate that with a simple exponential form. Minus EC minus EF. We put a minus here. Okay. Alright. Then the integral also approximates as 0 infinity minus y times square root y times exponential minus y divided by e. Why? This is solvable. It can be solved. And the number is half of square root pi. Oh, so you need to pull out the things out first. Sorry. So in this way, you can further pull out the term of E out. So that will be E over plus. Okay, E powers B 0 to infinity y E minus y. And this term is equal to half of square root pi. Alright. This is solvable. You should learn from the calculus. So that's the reason why we pull out the constant with 2 half of pi divided by square root pi here. Because when we are approaching something called the Boltzmann limit, that means the EF is still below the EC for fewer kT. That's a pretty common case. The integral value of half of square root pi half of 2 will canceling that out. So it will only leave the rest of the constant here. Nc is equal to 2 times mkt divided by 2 pi h bar power 3 over 2. This is a constant. Yeah, since you have the only variable is here, effective mass. And the surely temperature is a constant, but usually at least for this class, we always assume T should be 300K. Yeah, since it's not the purpose of studying thermal physics yet. Okay, so the NC, we similarly we can pull the content out. So this is important for you to do the homework. You didn't need to calculate everything again. So now this will be useful. For example, I will tell you the MC is 0.0667 eV. Then you only need to put the number here. Then directly find the density of state. And this constant is called the effective density of state. Then the N can be approximated as such effective density of state times exponential EF minus EC. But remember, while you use that, you need a mindset that this is under the assumption that EF is much lower than EC. But in next class, we will see what happens if you have a high carrier density when EF is approaching to EC. This relation doesn't hold. We also need numerical methods. Okay, anyway. Alright, so under equilibrium, since the EF is below far below EC, we can have the exponential term of the carrier density. Similarly, if it is in 2D, we don't need to do such assumption because the integral is solvable. We will see that this is the constant we pull out, and this is the Fermi-Dirac distribution times dE. And fortunately, we can directly integrate that, and we have an exact expression like this. All right, but it can still reduce the two. So this is the exact solution. But there's a case if also EF is much smaller than your ground state. Okay, I have to check the color. Since in 2D case, your ground state looks like this. And this is your ground state energy. So when the EF under equilibrium is still less than your ground state. So this term is very small. It can be approximated as long is reduced to x. So the N in the quantum well case, it could be still written in the case of a Boltzmann limit when under equilibrium. it will be NC quantum well, but this will be a different number from the previous case. Also times divided how far is the ground state away from EM is also the exponential decay. Alright. And the effective density of state in 2D is written like this. Yeah, you can just double check. Yeah, NC is written like this. Then also all constant will pour all the necessary constant out and package it together. It will be 1.08 times 10 powers 20 times effective mass of electron or hole, depends on your calculate what you're calculating. Times T divided 300 and 1 divided by D. Okay, we have practice later. And for the force things, we have only one Fermi level, but we have two bands. So okay, I will show you the other side. And this is the EF. Higher than that. However, for the heavy hole, since you two hole have two different effective mass. One probably looking like this. One is this, and probably the other one has a lower density, a different density of state. So you have a different ground state for that hole. So you need to calculate that separate. Then adding them together. This is because the conduction only have one band, you don't need to consider that. However, for the valence band, you need to calculate the heavy hole, light hole, and speed of hole separately. If I give you a Fermi level, then add them up together. But lucky, in practice, you will find the most of hole are heavy hole, because the effective mass is high. So this is also part of homework. You need to calculate in the homework. You need to calculate the position of heavy hole and the light hole, and tell me how many holes in the hole are heavy hole and how many holes are light hole. I will show you that later. So anyway, the total density of hole can be written like this. So this part is these are common constant, and this M means the effective mass. M star is the effective mass. It can be heavy hole or light hole. And here's the N, because while you are between E1 and E2, the density of state has a constant. So you can calculate that for 1, you calculated the density of state first, and if your energy is larger than the second level, then you can pull out another string but with a different reference level. Then do the integration again and summon it back. But fortunately, we will not encounter this case for most of the time because the population will be really few compared to the band in the first level. Alright, so here's the real calculation about evaluating the energy absorption for the quantum wave. So let's consider a 3 nanometer gallium nitride is sandwiched between bulk aluminum and nitride. For simplicity, we assume that the effective mass of the aluminum and the gallium nitride are the same, and the band of say is followed. Delta EC over delta EG is 0.66, and delta EV over delta EG sure will be 1 minus this number, so it will be 0.34, and the effective mass of the electron is and 0.067 m0, and the effective mass of 4 is 0.47 m0. Calculate the density, carrier density in the position of Fermi level under equilibrium. Because we can calculate under non-equilibrium in that case. Okay, so for the E1 by percent, we are not going to repeat that. The result is that N1 is 197 MeV above the EC. And if you repeat the same procedure with different effective mass, you have the EP1 is 92.5 MeV. Yeah, you can try that by yourself. The procedure is totally the same. Just try another. You just try with different the depth and the different effective mass. All right. And remember that while we're doing the approximation, we always assume the edge, the local energy 0. So while you get this number, you can imagine that we turn this image 180 degrees. So it flips. So the 92.5 MeV represents the distance between your ground state and your EV. And surely the ground state should be the EV and below that, below 92.5 EV. So for quantum wheel, the band edge absorption is actually larger than your band gap because you have a confinement state. Your ground state is now no more EC. For energy between EC and the EN1, the density state is 0. So there will be no absorption. The energy is large enough, but there is just no state. So the minimal band edge absorption will be from EP1 to EN1. The band gap, the band edge absorption of such quantum will blue shift, then its band gap. And the difference will be the ground state between that. So this is the quantization effect of the quantum wheel. The absorption edge will blue shift. And the thinner the quantum wheel, the energy level will be squeezed out of them. You can also try to see that in the given examples. Alright, so now we know the position, what the position is. Then we can try to find the Fermi level by equating both sides. So N is because the EF is still in the middle, we can just approximate that N is NCQW exponential minus EN minus EN over KT. And the P is the same, but you see, because the integral is 1 minus f, so the position of this will shift. It's no more En minus Ef, it's Ef minus Ep. Yeah. I think this is so. If you take the statistic of the semiconductor, you will understand that. Alright. Then we can calculate the NC and the NV with different effective mass. So for a material with a larger effective mass, you should have a higher density of state. 有效质量大的材料，它的那个 density of state 会大。所以 gallium nitride 跟 aluminum nitride density of state 它们的 effective mass 都很大，所以它们density of state 比较大。相对的，那个 gallium arsenide 或 RMP 那种小 band gap 的材料，你的那个 effective mass 小，所以你的density of state 自然也会比较小。这个概念我们会不停的讲，应该到这个 这个到期中考以前，你一定要把这些东西要在写定。Alright, so we calculated that the effective density of state in the conduction band is around 2.41 times 10^18 per centimeter square, and the angular is larger because they have a higher density of state. It's something like that. And the equate both sides. Something like that. And after few rearrangement, you just put this here and divide it here, take a log at both sides. The Fermi level should be something in the middle of the first ground state and the in conduction band and the invariance band plus KT natural log NV divided by NC. Alright, since you have calculated that, you can just put it in. Alright, so it should be somewhere in the middle of N1 and the P1, then plus 53 EV. It should be somewhere in the middle, then plus 50.3 MeV. So if that is that. So the En1 minus the Fermi level will be half of the distance. I will just draw. So it's En1 EG1 and EC EB. Alright? This is the middle of half of N plus P. And it's above that. This is your final Fermi level. And this distance is 50.3 MeV. Alright? So the position surely in the middle of the En and the P1, below that is actually already a correct answer. But since we didn't know where the En and the EP at the beginning, you shouldn't express me an answer like this is not good enough. It should tell me how far it is from EC or EB. That should be the right answer. Yeah. Alright, so this is 1.42. This is the band gap of the gallium arsenide. This is the band gap of the gallium arsenide. And plus 100 and 190 is the band gap of the alright. This is the band gap of the En1 to the EC. And this is the band gap of the E to EB. And the minus, and so this is the position or in the middle of the band gap, because I'm referring that to the En. I think this is not a good answer because I already assume where the En is. I will give you a new version, assume where it compares to the EB or this. Anyway, so the answer is the Fermi level is 712 MeV below the first ground state, and then you put back to your relation here, you will get a carrier density only 2.5 10^6 cm minus 3. This is not a practical value, it is too low. The reason is if your crystal is perfect, theoretically, you have a very high carrier density state for a 1.4 eV material. So at the beginning, people indeed think the wide bandgap material should be not semiconductor because your carrier density will be very low. You can assume the number something like 3 here. The carrier density probably only 100. Now that's practically impossibly low for a big solid. So why does this model doesn't apply inconsistent with the real case? If you take a good piece of gallium arsenide and try to measure its carrier density, the carrier density is still probably 1 million higher than this number. That's because we always have some point defects in the crystal. So those point defects act like doping. So even intrinsic material, that means you're buying a material and trying to get it clean as possible. We didn't really write it down as U-type. It's usually called UID. Unintentional非故意掺杂这个 UID。That would explain why most of the semiconductor, even in U-type, the carrier density is not as low as you think compared to the field. Yeah, because you always have some like vacancy to compensate or to lower the total energy. Yeah, that's another story. But while you are trying to calculate that, it's your homework. You don't need to consider that much. You just calculate the number, and I will show you whether you apply the theory correctly.